Today I'm going to be talking about such a cool topic in math, and what we're going to be asking ourselves is what really is the dot product, or what really is the scalar product between vectors. Because most of us first meet the dot product in high school, and it's this classic formula. You have two vectors, x and y, and you do x dot y, and this dot product, if x is a vector like 3, 4, 5, and y is a different vector, 1, 1, 2, well, the dot product between them is just the product of each component. So x1 y1 plus x2 y2 plus all the way to xn yn. So in this case, the dot product would be 3 times 1 plus 4 times 1 plus 5 times 2. That is the classic definition of, that is what the dot product is. And then with it, we can define angles, we can define distances. The distance is just the dot product x with itself, and that would be the distance squared. I mean, it's such a classic concept, and it doesn't seem very hard or very complicated. But what if I told you that what's going on underneath is actually much, 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 much deeper, and the dot product is just a special case of a more general thing called the inner product. The inner product is what we're actually talking about. And an inner product is just a function that takes in two vectors. So the inner product, we usually denote it like this. This is the inner product between two vectors. You put a vector here and a vector here. This is the symbol for the inner product. And it takes two functions. So, two functions, or it takes two vectors, and it outputs a scalar. So that is exactly what's happening here. The inner product, the dot product takes two vectors, and it outputs out a scalar. And there are some rules that define an inner product, and we're going to see what these rules are. They're very simple, and then we're going to see how this over here is just a really, really simple generalization of what the inner product actually is. We call the dot product just a very simple generalization, and it looks very simple. But actually, what's happening underneath, the reason it's simple is because we calculate the inner product using an orthonormal basis relative to our standard the definition of the inner product. I know all this sounds a bit crazy, but just imagine you had a Christmas dinner, with your family or your cousins, and you ask them to tell you what they know about the dot product, and they're gonna say it's this over here, and you're gonna be laughing, and you're gonna say, well, actually, it's a little bit more complicated like that. The dot product, or the inner product between any two vectors, x and y, is actually x transpose times g times y conjugated if we're in the complex plane. If we're over the real numbers, it's just y. This, when we're talking about the dot product or the inner product between vectors, what is actually happening is vector matrix multiplication, where x is just a column, where x is a vector, and transpose just means we turn it into a column. So we're going to have x1, x2 up to xn, and y will just be a classic column vector, so y1, y2 up to yn, and x will be a row vector. And G is the Gram matrix, which is the matrix of all the dot products of the basis vectors with each other. This is how, you're going to see in a second, it's going to make a lot of sense, but this is how it's actually defined. And it turns out that when we're using an orthonormal basis, which I'm also going to explain in a second, when we're using an orthonormal basis relative to a specially defined inner product, the Gram matrix just turns into the identity matrix. And then what we're left with is that the dot product, which we usually denote like this, xy, or here, usually it's denoted like this in high school, but the inner products are actually denoted like this. It's just the same thing, will just equal x transpose y. And of course that makes sense. If we have x1, x2 up to xn, that's x transpose. It's just the column vector of x, flipped on it falls on the ground. Then we have the column vector y1, y2 up to yn. Well, then we obviously know that the classic, vector matrix multiplication, you just multiply, this row just multiplies by this row, such that, this multiplies by this multiplies by this, plus all that. So what we're going to get is exactly x1, y1 plus all the way to xn, yn. This G usually disappears because our standard basis is an orthonormal basis, but actually this is how the dot product is really defined. It is really cool, so I hope you're going to enjoy the video. Now we can slowly start getting into it. First of all, what do I mean that we can define the inner product in different ways? Or actually, first of all, let's actually, I'll tell you what the inner product first is. It has a few rules. The only rules of an inner product is it has to be linear. It has to be linear in first slot. And what I mean by that is just simply that if I have two vectors u, if I have two vectors u plus v, and I take their inner product with w. So in classic notation, this would be a vector. U is a vector, v is a vector. You add them together, and then you take the dot product with w. But we don't use this high school notation. We use this over here. That is just the same as taking the inner product with u and v plus the inner product with v and w. So I can just split it up, and that means it's linear in the first slot. And also, if we have a scalar, so just a number, alpha u, the dot product with v, well, I can take this scalar out. This can just be a number like 5, 6, 7. I can just take this out. I can have alpha u v. That is what it means that it's linear in the first slot, and it's gonna be semi-linear in the second slot. So semi or conjugate linear in the second slot. And what that means, again, this also holds. The only thing that's a bit special is if you have your dot product between u and alpha v, if you want to take alpha out, what's going to happen is you're going to take the conjugated transpose of it, and you're going to have not the conjugated transpose. You're just going to take the conjugate. You're going to take you're going to conjugate alpha. But this is only true if you're over the complex field. If you're over the real field, if alpha is a number like 5, then you can just take it out normally. If it's a complex number like 5 plus I, then when you take it out, it's going to become 5 minus I. That is just those are the rules. And then the only other rules is it has symmetry. So basically, the dot product between u, v is the same as the dot product between v and u if you're in the real numbers. If you're working in the complex numbers, there's a transpose over here. So uv is the same as a transpose of vu. But again, over r, it just equals. And it's positive definite. And what it means that it's positive definite is if you have two vectors and you take their inner product, then this has to be greater than or equal to 0 if, of course, v does not equal to 0. That is. These are the rules of the inner product, and lots of things can satisfy this. We can define an inner product in a lot of ways. Usually, how we define the inner product is, the standard way to define the inner product is we have two vectors vu, and how we define it is just that you multiply each vector with its own component. So, or actually, the classic way, I just have it in my notes, is xy. So how we define it is just x1, y1 plus x2, y2 plus all the way to xn, yn. And you think, all right, well, that's pretty simple. So I guess, we can define the inner product in different ways, and I guess you can define it differently, but how we usually define it, that's how it is. No, it is a bit cooler than that, because if we define it this way, if we define our inner product this way, it doesn't mean that if you have two vectors, and if they're not expressed in an orthonormal basis, your result x, xy will still be x transpose g times y conjugated, or just normal y if you're in the real numbers, where g is the Gram matrix, and it's going to be the matrix of all the inner products of your basis vectors. And only if your basis vectors are orthonormal will g be the identity matrix. So you're going to see what I mean by this in a second. But let's say we define an inner product like this, and now we're going to see why. If we define the inner product like this, and if we have two vectors x and y, and they're not expressed on an orthonormal basis, why isn't this actually our inner product? You will see in a second. First of all, what is an orthonormal basis? Orthonormal basis just means that all the vectors are perpendicular to each other. So the classic orthonormal basis, which I'm talking about, let's say we're in R2, well, the classic orthonormal basis is this one. We have this basis vector and this basis vector. This guy is the classic 1, 0, and this guy is the classic 0, 1. This is an orthonormal basis because they are perpendicular to each other and they both have length 1. In R cubed, in a three-dimensional space, we'd have this vector, and this vector, which would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are orthonormal basis vectors, length 1, and all perpendicular to each other. Now let's imagine that we don't have an orthonormal basis, and we define our inner product like this, and let's see what happens. So first of all, let's just define a basis. We have a basis, and this basis can be b1, b2 up to I have to do 3 dots, up to bn, and this will be a basis for v. So for our basis for our our vector space v. Now we with this basis, we know that we can express, if we have the inner product x and y, we know that actually we can express our vectors x and y in terms of their basis. X is a vector, x is a vector with components x1, x2 up to xn, and but all these components are expressed in the basis. This is the basis b1, b2, bn. I made this in a previous video, but vectors are always expressed in terms of a basis. We usually don't notice that because they're expressed in terms of a standard basis, but these all could be basis vectors. B2 could be a basis vector 5, 7, 3, 9, if we're in a 4-dimensional vector space. So it would be x2 can be 5 times all of this. This would be, it's not, usually the standard basis is 0, 0, 1. So let's say if we have a vector 5, 6, 8, then 8 would just be 8 times 0, 0, 0, 1, and we wouldn't notice. I made a whole video on this and it's really cool also, but basically we can express every vector in terms of its basis. So if we want to express x in terms of its basis, it would just be x1 times the first basis vector plus x2 times the second basis vector plus all the way to xn and the nth basis vector. Again, if you want to know about this a bit more, there's cool YouTube videos on it. I also made one. But y, of course, can also be expressed in its own basis. So y is y1 times the first basis vector plus y2 times the second basis vector plus all the way to yn and the nth basis vector. So when we take the dot product between x and y, what we're actually taking, the dot product between x, y is actually the same thing as the dot product between this and this over here. So x1, b1 plus x2, b2 plus all the way to xn, bn, and this is our vector x, and this we're taking the dot product with y, which is y1, b1 plus y2, b2 plus all the way to yn, bn. This is the dot product, the inner product we're taking between x and y. Now remember how we defined that the dot product is linear. And if it's linear, if you have two vectors, u plus v, and you take the dot product with w, you have to split it up. So what happens here? Here we have, these are all coefficients, x1, x2, xn, these are all scalars. B1, b2, bn, these are all vectors. These are basis vectors, and they're all vectors. So this, again, this is a vector times a scalar, this is a vector times a scalar. We have to split all these up. So this, you're gonna see, why it gets a little bit complicated now. Like this inner product. First of all, let's focus on this guy over here. I can highlight it. Let's focus on this guy over here. Well, this, if the inner product is linear, this has to be taken the inner product with every single value over here. So what we're gonna have is this equals x1 b1 inner product with y1 b1, and then we move on to y2 b2. So we're gonna have plus the inner product with x1 b1 still, and y2 b2, and then we keep on moving up to the final term. So we're still with x1 b1, and we take its inner product with yn bn, and now we can finally move on to the second term over here. And now the second term has to be taken the inner product with everything here too, because again, the inner product is linear. We can split it up. We have to split it up. So what happens is we get plus x2 b2 inner product with y1 b1 plus x2 b2 inner product with y2 b2. And again, this is when you start to realize, again, x2 b2 yn bn, this is when you start to realize the dot product is actually a very, very long operation. Here, we haven't even defined what the dot product does. Again, this this dot product is defined to do something. Usually, we define the dot product to take the standard dot product definition is if we have x and y, we take the we just do x1 y1 times x2 y2. But again, it looks simple, but when we express this in terms of a basis, then this over here, well, these are again two vectors. And we can express this further again, so we get another whole n times n matrix inside of here. You're gonna see why this kind of gets cleaned up in a second, but we haven't even defined we're taking this holds for any inner product. It can be defined completely differently. We can define an inner product xy such that what happens is what happens is 5 x1 y1 plus 3 x2 y2. It can have a different definition, but this. We haven't even decided on the definition yet. We're still just, expanding the inner product with our basis. So again, let's say I do this for everything, and now I have to move on to the last one. So I just add on a bunch of terms, and the last term I add, the last part of the terms I add will be xn bn, and I have to take the dot product with y1 b1, and then again, xn bn, I have to take its dot product with y2 b2, and the final term in this very matrix product looking like thing will be xn bn with yn bn. Again, any linear algebra student will say, well, this is starting to kind of look like a matrix product, because we have rows and columns, ones and twos. Well, we are definitely getting there. Linear algebra is absolutely everywhere. That's the cool thing. Like, you know, a simple thing like the dot product, linear algebra comes in very perfectly. So now we want to take these scalars out. Again, we said these, you know, x1, y1, these are all scalars, so I can take them out. I can take x1 out normally, and you know, if we're over the complex plane and I want to take y1 out, then I have to take its conjugate. Those are the rules. So now we can start taking out these scalars, and I'll take out x1, and again I'll take out y1. I'll pretend like we're over the C field, so I'll take the conjugate of y1, but if we're in R, you know, the conjugate, it can just disappear, and we'll have the inner product between b1, b1, and then of course, plus I take out x1 and y2, and I'll have x1, y2, apply the rule here, pretending we're in C, and then we'll have the dot product between, and the inner product between b1 and b2, plus all the way I take x1, yn out, and then I take the inner product between b1 and vn. And I'm just gonna skip the video and finish all this up. Okay, so I just wrote all this out. This is what we're left with. Again, we take all the scalars out, we get this over here. The dot product between x and y equals this over here, where, you know, we express where x1, y1, these are just the coefficients of these vectors, and this is the basis where the vectors are written in. Now, what we're going to see is, you know, anyone with any linear algebra knowledge is going to say that this looks very familiar to kind of matrix, vector matrix multiplication. Now, what we're going to do is we're going to not focus on the scalars right now. We're just going to write down these, you know, these inner products, and we're gonna kind of stack them into a matrix. So we're gonna have b1, we're gonna have the inner product between b1, b1. Then we're gonna have the inner product with b1, b2. Then, and you know, at the end we're gonna have the inner product. I'll draw this a bit closer to each other actually. So yeah, b1, b2. Here at the end I'm gonna have bn. I'm gonna have b1, bn. And now again, I'll skip this video and I'll just draw this whole thing out. Okay, so this is what we'll get if we stack them on top of each other. And now you can see that I can turn this into a matrix. We put, you know, the matrix symbols around this, and we call this now the gram matrix. You know, and the gram matrix, the G, you know, the gram matrix represented by G, the ij, so you know, the ith row and the jth column of it will just be the inner product between your ith basis vector and your jth basis vector. So you know, if we have 1 2, g 1 2, you know, first row, second column, it would just be the inner product between the first and the second of your basis vectors. This is what the gram matrix is. And now we can see, you know, this is just to make all this, you know, to make all this long addition kind of simpler. So what we do now to actually add in the scalars, we're gonna see, well, y1, y2, yn is all multiplied with b1, but you know, b1, b2, b1, bn. It's, you know, y1, y2, yn are multiplied by all these top columns. We're gonna see that if we put this vector y, if we have it in the column vector up to yn, we're gonna see that this is exactly what we get. You know, with vector matrix multiplication, you multiply this column by this column, and you get exactly y1. You get exactly y1 times b1 plus y2 b1 b2. You know, in the first column, exactly what we want here. And again, if we're over C, we have to take the conjugate, but that is not, you know, this is just so we're really formal about it. But x1, x2, xn are multiplied on this side over here, so we can't just put x over here. This is why we take the transpose of x and move it to the other side. You know, in the definition that I showed, you see now that it all makes sense. We take the transpose of x and put it on the other side of the matrix, so we have x1, x2 up to xn. Now you're going to see with this definition, we multiply all these by these, and we get a vector, and then the final vector we get, you know, we're going to have a special vector here, then we just multiply all these rows by all these rows, and we get exactly what we want. We get exactly this sum over here. So the inner product between x and y will exactly just be, you know, in shorthand notation, the inner product between x and y will exactly just be x transpose times g times y, or, you know, y conjugate if we're over C, where G is the gram matrix. So this is the gram matrix, and you know, the gram matrix is just your definition of the inner product applied to every single one of your basis vectors individually. This is what the inner product actually is. And now notice the most beautiful thing, because again, why, oh, like this seems pretty, you know, why is a normal inner product, you know, the one we're used to, so simple? Because again, even, well, what happens is, if we have an orthonormal basis, if these are orthonormal basis vectors, an orthonormal basis is defined such that all the vectors are perpendicular to each other, and any inner product, no matter your inner product definition, if you take if you take the inner product between two vectors, between, let's say, two basis vectors b1 and b2, and if they're perpendicular to each other, the inner product must be 0. And if you take the inner product between two orthonormal vectors, so they're both length 1, and if they're exactly the same vector, then your inner product has to be 1. Based on that definition, the inner product, this always has to hold. So notice what happens over here. Here, b1, b1, b2, b2, bn, bn, these values will all be 1. But here, all these vectors on the sides are perpendicular to each other. So what G will turn into, it's going to be a matrix with 1s on the diagonal and zeros everywhere else. It will be exactly the identity matrix. If we use an orthonormal basis, the Gram matrix will be the identity matrix. So then the inner product xy will be exactly, the inner product with x and y will exactly be equal to x transpose times I times y, y conjugate if we're in the complex plane, and I has no effect on it. We can just remove I. The identity matrix doesn't change anything. So this is what we're left with. This is how we get back to the clean definition of the inner product, of the dot product. And again, here notice that this, I can define the inner product differently, but if I choose an orthonormal basis based on my specific inner product, I will always get this definition over here. However, not, this is where it gets a bit confusing, because how we usually define the inner product, I guess we would just, x, how we usually define the inner product with the inner product between x and y is just x1, y1 plus x2, y2 plus all the way to xn, yn. With this inner product, it so happens to be that our standard basis, so our basis vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. It so happens that these vectors are an orthonormal basis to this definition of the inner product. If we use this definition of the inner product, these standard basis vectors, which we always use on Rn, in high school, you always use this basis. You never use any different basis. It so happens that with this basis, that this basis, with this definition of the inner product, is an orthonormal basis, which is why, this is the classic definition of the inner product, this is the classic basis we use. That is why, with this definition, we get such a simple component-wise dot product. If we still had this same definition, if the definition of our inner product was still exactly this over here, but we didn't have an orthonormal basis, we had different basis vectors. Let's say we were just, we were in R2, but this wasn't our basis anymore, so, I can just draw in one color. Let's say our classic basis vectors are this, but let's say I chose a different basis. Let's say my basis vectors could be this guy and this guy. Well, then, if I express any vector, if I have a vector here, usually I express in terms of the classic basis vectors. Well, then I just express it normally. So 1, 2, 3 times this basis vector plus 1, 2, 3 times this basis vector. But in my different basis, I could express it as 1, 2 times this vector plus, let's say, 1 times this vector. Let's just say it works out. But if I use a different basis, then even with this classic definition of the inner product, I would have to do component-wise, the inner product would be the component-wise of every single value here. So it wouldn't be that only the diagonals remain. If I have this inner product, and if I have vectors, if I have a vector, let's say, if I have a vector x1, x2, so just a two-dimensional vector, and I take its inner product with y1, y2, with this definition, if we're not in an orthonormal basis, it would be x1, y1 plus x2, y1 plus x2, y2 plus x2, y1. I'll have to, this will be my inner product. Usually, with this orthonormal basis, these two are 0 and only these two remain. But, that doesn't have to be the case. With this definition, that definitely does not have to be the case. And that is kind of, that is such a subtlety that, no one in high school, of course, you'll never realize this, but it's kind of crazy. You actually realize that, oh, this is how we usually define the inner, this is the standard inner product definition. This is the basis I'm using. This is why this is why the inner product is just x1, y1 plus x2, y2. Even if you keep this definition, if you switch bases, the inner product will be, you will have this computation with every single component of the vector with each other. You have such a beautiful computation because you've been doing these products in such a simple matrix. Now, the last thing I still want to cover, because again, some people might have noticed this, is what happens, because of course here, I went through this whole long journey of expressing x and y in their own basis vectors. Well, b1, b2, these are also basis vectors. So, what do we say when we're doing this expression, b1, b2? Well, can't I also express, b1 and b2? These vectors are also just vectors expressed in a different basis. So, if my classic inner product definition between x, y is still x1, y1 plus all the way to xn, yn, but why does this not get its own matrix? Well, it actually does, but b1 would just be, b1 will be a basis vector expressed in the standard basis. We always, at the end, we can express, our basis vectors are then at the end of the day always expressed in the standard basis. So b1, can be the vector, let's say, b11 e1 plus b21 e2 plus, plus all the way to bn1 en. So where b11, b21, bn1, these are coefficients, and these are the standard basis vectors. And the standard basis vectors, of course, are e1 would be 1 0 0 0 all the way to the end, and en would be 0 0 0 all the way to 1. We express these basis vectors in the standard basis, and if we do that, of course, this basis is orthonormal relative to this, so our gram matrix would just be the identity matrix. So when we take the inner product between b1 and b2, of course, we would get b1 transpose times the gram matrix times b1 conjugate, but we're working over the real numbers right now, so this disappears. The gram matrix is exactly the identity matrix, so we just get b1 transpose times b2. Here is supposed to have b2, and this is exactly just, again, this would just exactly be, this b11 up the way to bn1. This would be the b21 b22 all the way to this, and we'd get the classic component. So now, because they're expressed in the standard basis, this special definition over here, I mean, we don't get a whole another deep matrix inside of the matrix. This is now really just the normal, this is just now the normal standard basis vector. When we take the inner product with this definition, again, these are expressed in the standard basis, this is why we just get the classic normal definition that we defined at the start. But if our vectors were not expressed if our general vectors are not expressed in the standard basis, our vectors are expressed in some basis b. This basis b, these vectors are expressed in the standard basis, but our basis isn't. So then again, I guess we get this whole complex layer, and the inner product between x and y will be this over here. And then again, this is just how we define the inner product is by defining G. Again, we have G. G has some properties. If you want to define an inner product, again, you just define this matrix G. Let's say I want to define the matrix G as having, 5, 6, 8, 3, 2, 9, 1, 1, 2. This actually wouldn't work. G has to be such a matrix that if you take the transpose, and then if you conjugate every term, and if you then conjugate every term, it has to be still the same thing. So G has to be Hermitian. If we take the transpose, the conjugated transpose, this is just the same thing as saying GH. This still has to equal to G, and it has to be positive definite. I won't really get into this now, but you have to have a matrix that satisfies these conditions if you want a valid inner product. Again, I stated out the rules of the inner product. Those rules transform to having a special matrix like this. But let's say this matrix satisfies all these rules. Well, then this is how I define an inner product. Then when I have an inner product between x and y, what I just do is x transpose times G times y conjugate, where G is this matrix over here. And again, that just means that with my basis vectors b1, because this matrix G is just my my defined inner product b1 with b1 itself. So let's say I say that the inner product with my basis vectors has to equal 5. And then, the inner product with my first basis and my second basis vector has to equal 6. This is how I define an inner product. And then again, if I know what the inner product does to my basis vectors, well then, then the whole inner product is defined, because again, what happens with different vectors? All that happens is I add these coefficients to my results, So then if I know what my inner product does to the basis, then of course, when I have x and y, I just add special coefficients to these inner products, and that's how I change the result. That is kind of some more deep intuition of what the inner product actually is. I hope it made sense. I hope the video wasn't too long. But yeah, now, when you're in Christmas dinner and you want to show off to your cousins about what you learned, you can ask them what they know about the scalar product, and you're going to show them that x, y actually equals xt, g, y conjugate, and they're all going to be like, wait, what? That's not the scalar product. The dot or the scalar product is just, it's just that. And then you're going to say, oh, well, that is a very specific generalization of the inner product, where you define the inner product as just component-wise multiplication, and you use an orthonormal basis relative to that inner product. Bang, their minds are going to be blown. Thank you for watching. That is it. Make sure to smash that subscribe button and see you next time.